So this problem up here is practice of the stuff that we were doing yesterday. Now we're starting with one that's hopefully at least a little bit more on the straightforward side. Remember that the key thing that we learned yesterday was that if we have an x that's both in the base and in an exponent, that we have to start by finding the logarithm of both sides, specifically the natural log of both sides. So I'm going to go natural log of y equals the natural log of x to the power of 4x cubed. And the whole reason why we do that is because the logarithm rules allow us to pull that exponent out. So I can turn that into 4x cubed times the natural log of x. Once we're here, we now can use our implicit differentiation rules to find our derivative. So on the left side, it's the natural log of y, so the derivative of that is 1 over y times y prime. Or you could have written it as y prime over y. And then on the right side, though, notice we have to use product rule. Specifically, 4x cubed times the natural log of x. So derivative, let's do original times derivative plus derivative times original. Order doesn't matter. Some of you might have done it in a different order, but since we're adding, it doesn't matter. So I'll do original times derivative, so 4x cubed times derivative of natural log is 1 over x plus, now we do derivative times original, so that's going to be 12x squared times the natural log of x. Now I still want to solve this for y prime. So that means I'm going to multiply both sides by y. And so we're going to end up with y prime equals y times 4x cubed times, 4x cubed times 1 over x. We can simplify that, can't we? Just make it 4x squared. Make your life easier there. Plus
12x ln x.
12x squared natural log of x. We do have one last step to go, though. We know what y equals. Remember, the original problem told us what y equals. So I'm going to go ahead and, on my last step, plug that in for y. And so we're going to go y equals x to the 4x cubed times that whole thing, the same as it was inside the parentheses before. And that's our final answer. So for doing this problem, notice we do have x in the base and x in the exponent. So yes, we still do need to solve this one by finding the natural log of both sides first. But when we do that, we got natural log of y equals the natural log of x to the 5x times 3 to the x. And right now, I cannot just pull out the 5x and I cannot just pull out the x. But I can deal with the fact that it's multiplying here. When I multiply inside the logarithm, I can turn that into addition outside of the logarithm. So this whole thing can become the natural log of x to the 5x plus the natural log of 3 to the x. By doing that, I've now made it into something that's much more workable. Now, again, we can go ahead and pull out those exponents now. So it's going to be the natural log of y equals 5x natural log of x plus, I'll go ahead and do it here as well, x ln 3.
You did not.
Now that we're at this point, we find the derivative implicitly once again. So when finding our derivatives, we got two terms, so we find the derivative of each term individually. For this first term, notice 5x times natural log of x. That's going to be product rule. So I'm going to do original times derivative plus derivative times original. Next up, I now need to find the derivative of this term. But for this term, I know some of you did it using product rule. But you didn't actually have to use product rule here. Because, let's say you did product rule here. Let's do derivative times original. So that would be the derivative of x is just 1. 1 times natural log of 3 is just natural log of 3. So that would be derivative times original plus original times derivative. What is the derivative of the natural log of 3? 0, because the natural log of 3 is a constant. And so if you use product rule, that's what your work looks like. You write a plus 0 there. But the plus 0 would suggest that maybe we didn't need it. And that's true, because you'll notice x times the natural log of 3, it's just x times a constant. And might as well have given you a problem that was like, what's the derivative of 5x? It's just 5, right? It's just the constant. What's the derivative of natural log of 3 times x? Natural log of 3. Same idea. All right, and then the last step in this problem is just to clean it up and solve it for y prime. So when we solve for y prime, I move the y to the other side. And then, yes, we'll substitute in what y equals. I'm going to go ahead and do that all at once here. So I'm going to do x to the 5x, 3 to the x, times, now 5x times 1 over x, that's just 5, plus 5 times the natural log of x, plus the natural log of 3, and we're done. Now a little hint on this one. If you started by taking the natural log of both sides, think about your choices. Now the reason why we do not need to start by taking the natural log of both sides is because, remember, we have to use logarithmic differentiation when we have an x both in the base and in the exponent. But notice we have x's in both bases but not in any of the exponents. And so we don't need the natural log of both sides for the logarithmic differentiation. We can just go straight to our work. Now, in looking at how we do our work, it's always good to think about ways that you can make your life easier, especially in math, right? And if you started by using product rule, I'll tell you there's an even easier way to do it that way as well. Think about, how could you do this derivative without using product rule? Heck, without even using chain rule. Well, as I look at this, I see a lot of polynomials. I mean, I could actually do the squaring here, so I could turn this into 9x squared. But then, can't I multiply the x's there? And if I multiply the x's, I just add their exponents. So that's what I'm really finding the derivative of. I mean, you can use all sorts of complicated methods, and they'll still work. But isn't it a lot easier to just do this? Look for ways you can make these problems simpler, and do so when you can. There's nothing wrong with simplifying it first. Now, first thing you did, I hope, was take a look and see what sort of method will we need to use. Do we need logarithmic differentiation on this one? Yeah. Because notice I got an x in the base, and there's an x in the exponent, so yes, we do need to start by finding the natural log of both sides. And of course, the whole point in doing that is so we can pull that exponent out. And this looks kind of weird because we got multiple natural logs in there. Is there a way that we can combine those natural logs? Make it simpler? Not really. Because the only thing we could do is actually go back to this. So, we're going to have to use product rule here with a little bit of chain rule as well.
Chain rule.
And so on the right side, we got to use product rule. So I'm going to do original times derivative. So that's going to be natural log of x times the derivative of natural log of sine x. Now, natural log of sine x, that's your chain rule part. So it's going to be 1 over whatever's inside the natural log. So that's 1 over sine of x times the derivative of sine of x. So that's going to be times cosine of x. Plus derivative times original. So 1 over x times the natural log of sine of x.
I think I got it. Oh, God.
All right, last step, we're going to be moving that y to the other side and replacing it with what y equals. So I'm going to go ahead and put that in first. So the sine of x to the power of natural log of x. And that's going to be all times this stuff up here. But I do want to simplify some of the pieces as I go. The natural log of x that I first encounter, nothing much I can do with that. But I can simplify 1 over x times cosine, because that would be cosine over sine. And cosine over sine, of course, is cotangent. So I'm going to go ahead and call that cotangent of x. Plus stays a plus, of course. Now, On this side, there's not much I can do other than just making it into a single fraction. So it's going to be the natural log of sine of x over x. And that's about all we can do with that. So now this would be considered done. And you'll notice here, our answers end up looking really ugly, right? That's what's going to typically end up happening when we have the x to the power of x kind of scenario. But at least we can do it. And at least we aren't presented with something where we think we can't do it at all. But yes, logarithmic differentiation typically gives you an answer that looks really complicated. So as you start approaching this problem, do we need to start by taking the natural log of both sides? No. Remember, the rule is that we do the logarithmic differentiation if and only if x is in both the base and the exponent. And you'll notice in this case it is not in the base. So how do we find the derivative? Well, in this case it's a chain rule situation. Because we basically have 7 to the power of something. So the derivative of 7 to the power of something is 7 to that same power, so it's going to be 7 to the power of x squared, times the natural log of 7. But since we have that function in there, it's not just to the power of x, it's to the power of a function, we then have to multiply that by the derivative of that function. And the derivative of x squared, of course, is 2x. And so then that is our derivative. And any simplification we try to do from here would just be reordering. It wouldn't be changing anything else. So you can go ahead and leave it like this, or you can reorder it if you want to make it look a little bit prettier. Now in this case, will we need to use logarithmic differentiation?
Yes.
Yes, we will. We have the x both in the base and in the exponent. So yes, we will. Now, when we take the natural log of both sides and then we pull that exponent down, you'll notice we have natural log of x times natural log of x. Now, you actually have a couple options right now. You can go ahead and leave this as natural log of x times natural log of x, or you can go ahead and combine those. If you chose to combine them, you would end up with the natural log of x times itself means squared. So you could also write it like that. Either way you do it, whether you use product rule from this line, or whether you use chain rule from this line, you will end up with the same answer. I'm going to go ahead and use that last line. Now I go ahead and find my derivative. So on the left side, that's going to be y prime over y, because remember it starts as 1 over y times y prime. I'm just simplifying that into y prime over y. And then I'm going to use chain rule here, so that's going to be 2 times the natural log of x times the derivative of natural log of x, which is 1 over x. Last thing, move the y to the other side and simplify. So that's going to be x to the natural log of x times 2 times the natural log of x over x. When we start this problem, are we going to need to use the logarithmic differentiation method? No, because we don't have an x in both the base and in the exponent. And so we can just go ahead and start taking the derivative using rules that we had all before we started this logarithmic differentiation stuff. So it's going to be y prime equals. Now, what rule am I going to need to be using here? Chain rule. Now, for some of you, chain rule gets really tough here. So, if you're not sure how the chain rule is going to work with this, instead of going straight to the derivative, rewrite it. We're going to call this the natural log of cosine squared, remember, means that the cosine is being squared. And so we're going to do cosine of x squared inside the natural log. For some of you, that makes it a little bit easier to follow. And if that's the case, rewrite it that way. But then go ahead and start using your chain rule to find the derivative of y. All right, so for using chain rule, we start with doing the derivative of the outermost function, which is the natural log. So that's going to be 1 over whatever's inside of the natural log, which is either cosine squared x, or you can write it as cosine of x in parentheses squared. Either way, it means the same thing. I'm writing it this way just because it's a little tidier. But now I need to multiply that by the derivative of the cosine squared of x. And that's where it gets a little bit tricky about how you write it. Because some of you, when you look at that, and you're trying to figure out what's the inner function, what's the outer function, it gets a little bit harder. Whereas if we're looking at it this way, it's a little bit easier to tell that the outer function at this point is now something squared, and the inner function is the cosine. So I'm now doing the derivative of cosine of x squared, so that's going to be 2 times that cosine, and then times the derivative of the cosine, which is going to be a negative sign. Oop, didn't leave myself room to write the negative. So it's going to look like that. Last step, let's clean it up a little bit. So you notice I have a cosine that would end up on the top and a cosine on the bottom. And so those would cancel each other out. So that would suggest that I would then have a negative 2 sine x over cosine of x. But you'll notice even at that point we can go further, because I got a sine over a cosine. So it's negative 2 tangent of x. And that is then our final answer.